Today's experiment is on radioactivity, and we're going to look at three different aspects of radioactivity. The first one is the effect of distance on radioactivity. Now, if you want to measure the amount of radioactivity that a sample has, you need a device called a Geiger counter. And a Geiger counter is made up of two different components. One is a counter, and the other is a Geiger-Müller tube. Here on the cart, I have a counter, an electronic counter, and this black device right here in this specific stand made for it is a Geiger-Müller tube. The Geiger-Müller tube has a very thin window in it. This window will allow radioactive particles to penetrate it. Inside the Geiger-Müller tube is a noble gas. It's either atoms of neon or argon, something like that. And if you bring a radioactive source next to the Geiger-Müller tube and it's emitting either alpha particles, beta particles, or gamma rays, they'll penetrate through the window, they'll strike one of the atoms of the noble gas that's in there, causing it to ionize. It'll turn into a positive ion and then an electron. They will ionize other gas atoms in there. The entire tube will therefore be filled with charged particles in an instant, and it'll register a radioactive event. If it's hooked to a speaker, you'll hear a click. If it's hooked to a counter, it'll count how many radioactive events are taking place. And what we're going to do in the first part of the experiment today is we're going to use a radioactive source of cesium-137. So in your data table, if you can write down in part A, radioactive source, you want to put cesium-137. This is the source that we're going to be using. And what we're going to do is we're going to try to measure how much radioactivity you get exposed to next to a cesium-137 source if we vary the distance. And the way I'm going to do that is I have this little tray here underneath our Geiger-Müller tube, and I'm going to place our radioactive cesium source in there. Right now the tray is placed in the third slot, and so what we're going to do is we're going to count how many radioactive events take place in 30 seconds with our radioactive source at this particular distance. Now, this is an old-time counter. It's an analog counter, and what you might notice is there's little rings of numbers here. These stand for the ones column, tens column, hundreds, thousands, and 10,000s. And so what's going to happen is the numbers are going to spin around as the radioactive counts are being created as they strike the Geiger-Müller tube. I've already set this up, and what I'm going to wind up doing is I'm going to wind up pressing the start button, and I'm going to count this for 30 seconds, and then we're going to register or read how many radioactive events occurred in that 30 seconds. So on the right, underneath the Geiger-Müller tube, I have our radioactive source, the cesium-137, placed on the third slot, and we're going to now count how many radioactive events take place in 30 seconds. This is not only a counter, but it also is hooked to a speaker, so if I press the speaker button, we're going to be able to hear each of the radioactive events as they take place. That's a lot of radioactive events. So I'm going to press the start-stop button, and we're going to count this now for 30 seconds and see how many radioactive events take place in the 30 seconds. Now if we look at our counter, we have a 1, a 4, a 7, a 4, and a 1. So this is the 10,000s column, so this is 14,741. So you're going to write down 14,741 in your data table for the amount of radioactive events that take place in 30 seconds when our sample is in the third slot down from the Geiger-Müller tube. I'm now going to remove our radioactive source from the third slot and move it down to the sixth slot. Now its distance from the Geiger-Müller tube is a little bit further, and then we're going to count it again for 30 seconds to see how many radioactive events take place during this time period at a further distance. I'm going to now reset the counter to 0. I'm going to turn on the speaker so we can get an audio indication as to how active the sample is at this distance. And then we're going to go ahead and count this now for 30 seconds. Now, at a little bit further distance, let's see what numbers we have. In the thousands place, we have a 3, then a 9, then a 7, then a 5. So the number of counts in 30 seconds at this further distance is 3,965. You can record that in your data table. Now I'm going to remove the radioactive cesium-137 source and move it from the 6th slot down to the 9th slot at an even further distance. And once again, we're going to count this for 30 seconds to determine how many radioactive events are recorded at this longer distance between the Geiger-Müller tube and the radioactive source. So on our counter, let's reset it to 0. And then let's turn on the speaker so we can have an audio indication as to how much radioactivity there is at this further distance. And then let's go ahead and count for 30 seconds. So at this further distance, the numbers we have on the counter are 1, 9, 8, and then 9. So the number of counts in 30 seconds, 1,989. That can be recorded in your data table. And by observing our data here, you can see that there is a relationship between the amount of radioactivity one would be exposed to and the distance to that radioactive source. For part B of our experiment, we're going to experiment on the effect of shielding on radioactivity. So I'm going to remove now our radioactive source, and I'm going to actually keep the same radioactive source for part B. So if you would like to record this in your data table, the radioactive source we're going to be using again is cesium-137. And what I'm going to do is I'm going to place the cesium-137 source into the 2nd slot below the Geiger-Müller tube. We're going to count this for 30 seconds to see the amount of radioactivity from this short distance. And then after that, we're going to measure the radioactivity with a piece of paper shielding the radioactive source from the Geiger-Müller tube, then a piece of plastic, and finally a piece of lead. So I'm going to reset the counter. I'm going to turn on the speaker so we can hear the number of radioactive events that are occurring. And then we're going to count for 30 seconds. So after 30 seconds at this distance, we have a 1, a 7, a 5, an 8, and a 3. So that's going to be 17,583 counts in the 30-second time period. Now, to act as a shield, I'm going to slide a piece of paper between the Geiger-Müller tube and our radioactive source, and then we're going to go ahead and we're going to count for 30 seconds and see what effect the piece of paper has on the amount of radioactivity that's being impinged upon on the Geiger-Müller tube. So reset the counter, turn on the speaker, and let's count now for 30 seconds. So with the piece of paper acting as shielding between the Geiger-Müller tube and our radioactive source, we have 12,730 counts over a 30-second time period. Now we're going to replace the piece of paper with a piece of plastic, and let's count for 30 seconds and see how well the plastic acts as a shield against radioactivity. Reset the counter, turn on the speaker, significantly less, and now let's count for 30 seconds. Now after counting for 30 seconds, we have 1,447 counts. So only 1,447 radioactive events measured in a 30-second time period using a piece of plastic as a shield of the radioactivity. Now finally, we're going to replace the plastic shielding with a piece of lead. And we will count for 30 seconds and see how well the lead affects the radioactivity as it tries to impinge upon the Geiger-Müller tube. Reset to 0, speaker on, significantly less, and let's count for 30 seconds. So with lead acting as shielding between the radioactive source and the Geiger-Müller tube, we have 699 counts over a 30-second time period. So now you can see the efficacy of different materials used as shielding to try to protect from radioactivity. So even with lead shielding, you can still see some radioactivity does penetrate through, reaching the Geiger-Müller tube, which begs the question, how safe are we in any environment near radioactive materials? Well, the fact is, we're actually always exposed to radioactive materials. The walls of this building, made out of concrete, have a lot of radioactive potassium. They're giving off beta- particles constantly. Every human being has radioactive carbon-14 in them. In fact, every living organism does. They're giving off radioactive particles as well. We're constantly being exposed to radioactivity, and even from other sources. This is a piece of Fiestaware that I got from my kitchen. Fiestaware comes in lots of different colors, as you may know. This is a classic orange color they have now. And if I test my Fiestaware with the Geiger-Müller counter, or the Geiger counter, not much radioactivity associated with that. But if I can find an old piece of Fiestaware with a really nice orange color, that's even better than the color of mine, isn't it? That's really good. And I test this with a Geiger-Müller counter. Ooh, that's a lot. A lot of materials in the old days used to be colored by using metallic or ionic salts that contained transition metals that were radioactive. This actually contains a uranium oxide that has a characteristic orange color. Because of its high radioactivity, they don't use it anymore, so this you don't find, and I don't keep that in my house. A lot of people used to have watches that would glow the hands and the numbers in the dark because they would have radium painted on them, a radium salt, and those would actually be radioactive as well. So there are lots of things around that do have some radioactivity. Really high sources are no longer readily available. But certainly there is some lower amount of background radiation that always exists. And that's going to be an important consideration as we move to part 3 or part C of our lab today. What we're going to try to do is determine the half-life of a radioisotope. And if we actually want to count how many radioactive events this particular radioisotope is giving off, we're going to have to account for the fact that there is general low-level background radiation that exists naturally. And so we're going to make a background radiation count first, and then we're going to wind up trying to count the amount of radioactive events given off from a sample containing radioactive barium-137M. Now for part C of the experiment, we're going to determine the half-life of barium-137M, which means the metastable state of the radioisotope barium-137. Before we do that, we're going to make a background count. In this part of the experiment, we're going to use the student counter, which is a SpecTech 360. It's attached to the same Geiger-Müller tube we saw in the previous parts of the experiment. And I've set the SpecTech to be able to count for 60 seconds, and then we're going to see how many radioactive counts there are with our holder for the radioactive sample empty underneath the Geiger-Müller tube. So I'm going to start counting now, and we'll let this go for 60 seconds. As we approach the 60-second mark, you'll notice that the red light is still on under count, so that means the counter is still counting, and when the 60-second time period is ended, it's going to switch to stop. So that means we have a background radiation count before our experiment of 25 counts per minute. We're going to run our experiment. We're going to take another background count at the end of the experiment, and then we're going to average our two values together to get an average number of counts per minute that we'll use as background radiation. Okay, to determine the half-life of barium-137M, which means a metastable state of barium-137, we need a source of it. And the actual source we're going to use is the same radioactive source from parts A and B in the experiment, which was a radioactive source of cesium-137. Cesium-137 has a half-life of 30 years. That would take us actually a really long time to measure its half-life. But when cesium-137 undergoes radioactive decay, some of it turns into barium-137 in an excited state, and that's called barium-137M. And we're going to try to measure its half-life. Now to do that, we're going to take a sample that has cesium-137 in it, and as it's decaying away, it's actually producing some barium-137. In this container is an ion exchange resin. And as I force solution through this with this syringe, it's going to actually exchange the barium ions out and attach or keep the cesium ions. So the only thing that's going to come out of the bottom when I pass solution through this ion exchange resin is going to be the barium. So we can actually separate out the barium ions from the cesium ions. We won't have to worry about any background interference from cesium-137. This is sometimes called a cow, and so as we try to remove the barium from the cesium, that's known as milking the cow. So I have a little container that I'm going to place my solution in. So as I push down, it's going to force a solution of barium ions out, keeping the cesium ions. And once I have my 6 drops of the solution, I'm going to now take this to my Geiger counter, and we're going to count this for a 10-minute period. I'm now going to place my radioactive sample under the Geiger-Muller tube, and we're going to count it for 10 seconds at a time, every 30 seconds, for 10 minutes. I'm going to start my counter and the stopwatch at the exact same time. So the count for the first 10-second period, 2,756 counts. So that goes under sample count at 0 seconds, counts per 10 seconds. Now let's get ready for the second count, which is the 30-second count. So the counts per 10 seconds at 30 seconds is now 2,438. You can record that in your data table. And now we're going to get ready for the count at 60 seconds. (2,219 counts per 10 seconds at 60 seconds. You can record that in your data table. And now let's get ready for the 90-second count. (1,849 counts at 90 seconds. And now we're going to be ready for the 120-second count. (1,682 counts at 120 seconds. And now we're going to get ready for the 150-second count. (1,495 counts at 150 seconds. Now we're getting ready for the 180-second count. (1,261 counts at 180 seconds. Now coming up to the 210-second count. (1,076 counts at 210 seconds. Now getting ready for the 240-second count. (1,001 counts at 240 seconds. Now coming up to the 270-second count. (842 counts at 270 seconds. And now coming up to the halfway point, our 300-second count. (775 counts at 300 seconds. Now coming up to our 330-second count. (621 counts at 330 seconds. Now coming up to our 360-second count. (571 counts at 360 seconds. Now coming up to our 390-second count. (548 counts at 390 seconds. And now coming up to our 420-second count. (448 counts at 420 seconds. Now coming up to our 450 second count. .379 counts at 450 seconds. Now coming up to our 480 second count. .364 counts at 480 seconds. Now coming up to our 510 second count. .324 counts at 510 seconds. Now coming up to our 540 second count. .273 counts at 540 seconds. Now coming up to our 570 second count. .235 counts at 570 seconds. And now coming up to our final count at 600 seconds. .210 counts at 600 seconds, and that completes the number of counts we're going to, or number of trials we're going to take for this one sample through 10 minutes. Now you need to go back a page in your data table because we have to make our second background count. I'm going to remove our radioactive sample, and I'm going to place an empty container into the Geiger-Müller slot, and now we're going to make a background count here at the end of the experiment. I've set the counter to count for 60 seconds, and now let's make a 60-second background count. And now for our second background count, we get 25 counts per minute. So you're going to average the first background count that we took before the experiment with our second background count, and we're going to get an average value. That number of background counts will need to be subtracted from each of your values in the data table to be able to calculate how many radioactive counts were actually given off by the radioactive sample and not just by the radioactivity in the ambient surroundings. So now that you've collected all of your data, let's look at the data table, see how we're going to analyze that. On page 232, you have completed the entire first column, which is the number of counts there are per each of the 10-second interval counts that we did over that 10-minute period. That's the number of counts per 10 seconds. The next column in the data table asks you to determine how many counts there would have been if it would have been a minute period. So to switch a count per 10 seconds into a count per minute, you have to multiply by 6. So if you multiply each of your values that you recorded in lab by 6, you can fill out now the entire second column on page 232, which are counts per minute. The next column is titled corrected CPM, or corrected counts per minute. What does that mean? Well, we know that some of those radioactive counts that we saw the Geiger counter detect are due to background radiation, so we have to subtract those out. So on the previous page, still in part C, you calculated what the average background radiation was in counts per minute. That number needs to be subtracted from every single one of your counts per minute values on page 232. When you do that, you now have the corrected counts per minute. Now, how are we going to determine the half-life of this radioisotope? Well, it turns out from the mathematics of radioactive decay that if you make a plot of the natural log of the counts per minute versus time, that graph will be a straight line, and the slope of that line is going to be related to the half-life as explained in the introduction. So you're going to be using Excel instead of Logger Pro to do this, and what you're going to do is you're going to have to take the logarithm of every single one of your corrected counts per minute. And we've done that before on Excel. All you have to do is in the cell type in equals ln and then parentheses put your corrected counts per minute, and it'll calculate the logarithm of that. You do that for every single one of your data table points. Now, what's the corresponding time you're going to do for that? You might think we might do that at 0 seconds, 30 seconds, 60 seconds, 90 seconds, because that's when we began each of the counts. But that actually would introduce a little bit of an error because our counting interval was 10 seconds. So if you say that was the count at 0 seconds, that may not be so accurate. So what we're going to do is we're going to take the middle range there, and the first 10 seconds of our experiment, we counted from 0 to 10 seconds. We're going to say that's going to be the count at halfway between those 5 seconds. Our second count was at 30 seconds, but it went from 30 to 40 seconds. So that means you're going to assign that count period a time of 35, which is right in the middle of that range. And you can see all the numbers on page 232 are really right in the middle of each of the 10-second interval counting ranges. So then you'll be able to select that data and make a graph of the natural log of the counts per minute versus plotted time, and the slope of that line will be able to allow you to calculate what the half-life of barium-137M is. Now, before you're done, you have some post-lab questions you have to complete, and I want to direct your attention to question number 4 because that's going to involve your data in today's experiment. Question number 4 says, what would happen to the value of the half-life if corrections for the background radiation are not made? If we didn't do that, would you have calculated a half-life for barium-137M that's too high, or would you have calculated a half-life that's too low? That's an interesting question. It's actually hard to try to figure out in your head. So I'm going to give you a way to do that, and I want you to do this calculation. So on your Excel spreadsheet, I want you to change the corrected activity, the number of counts per minute that have been corrected, back so that the background counts have not been subtracted. Correct all of those numbers. So now the background count has not been subtracted out, you're including it. Then I want you to regraph that, and then from the slope of that line, determine the half-life to see whether the half-life is greater or less if this error occurs. That should do it.